Hey, this is the first part of topic 8.12 AP Calculus, where we do the volume with washer method, revolving around other axes besides the x and y axis. Our learning objective is to calculate volumes of solids of revolution using definite integrals, and our essential knowledge is that volumes of solids of revolution around any horizontal or vertical line whose cross sections are ring shaped may be found using definite integrals with the washer method. In this first part, we're going to look at the geometry behind this washer method. We'll talk about what's going on and the approach we're going to take, and then we'll do some examples in parts 2 and 3. So let's talk about the geometry behind this washer method. If we have a function whose graph is like that, and then we have another function whose graph looks like that, and we want to revolve this around some axis, not the x and y axis. Recall when we did the x and y axis, we did one large rectangle and we generated a disk by revolving that rectangle around. And then we did a smaller rectangle and we revolved around the x-axis to do that. Well, it's going to be very, very similar when we do the washer method. We revolve around another horizontal axis or a vertical axis when we get ready to do that. But instead, let's say we're going to revolve around this line, y equals some number a. And so let's call this blue graph g of x and the red graph f of x. So we want to revolve this region R around the line y equals a. So we can approach this the same way we did. Go ahead and get rid of that R. We can approach this the same way we did. We can look at this as generating one large disk that is this distance. And then we can take out of that one smaller disk. It's getting a little cluttered. So what we mainly need is we need to find the radius of that larger and smaller disk. The large outside disk, whoops. And so what we need is an expression for this integral. Because the g of x is above in this case, the distance for this, and if we revolve that around, we're going to get this one big large disk. And out of that, when we revolve the smaller one in a few moments, we're going to take out this inside disk to create our washer. So here, the distance is going to be the top curve minus our horizontal line. So this height of this rectangle is going to be g of x minus a. If a is a negative number, of course, it's going to become g of x, which is this part of the rectangle, and then plus this distance a. But g of x minus a at the top minus the bottom is always going to give us this distance of this rectangle. And so when we want the volume of this one large disk, go ahead and erase the inside disk there so we don't confuse people with that. If we want the volume of this one large disk, that's going to be pi, and recall the radius we said is g of x minus a. And of course the width is dx, so it's going to be pi times the radius squared times dx. That's going to be the volume of that disk. Now let's look at the inside disk. Let's get rid of all this. I'm going to do a smaller. Now we're looking for revolve this one around because this is going to be the disk we're going to take out from the center of this larger disk that we just revolved. So I'm going to draw this smaller disk. Width is still going to be dx. I need the radius this time of this disk. And now you see the height of the rectangle. Let me go ahead and take this, unclutter this a little bit first. The height of the rectangle that generates the disk that we're talking about now is going to be f of x minus a. So that radius is going to be f of x minus a. And the volume of this smaller disk, this is the inside, this is the outside. The volume of the smaller disk is going to be pi times the radius of this disk squared times dx. And so to find the volume of the region R revolved around this axis y equals a, we're going to get the integral. We call this, let's call it x1, and let's call this intersection x2 that defines or bounds this region. We're going to integrate from x1 to x2, and this is going to be pi, this is going to be the outside first. It's going to be g of x minus a squared dx, and take out the volume of the inside disk, which is going to be pi times the integral from x1 to x2 of f of x minus a, squared times dx. If we're revolving a region about a vertical axis, it's going to end up being the same kind of thing, okay, around a vertical axis. Let's look and say that we have two functions, f of x and g of x. Well, that's not a function. Let's just go ahead and say this intersects there, and we'll call this x1. So in this case, it's intersecting at 0 and at x1. That's accidental, but it is. And so now let's revolve around the line x equals a. And so if we're going to revolve that, we're taking one large rectangle here. Well, let's do like we did before, and let's invert and get this to change. This is the x-axis, this is the y-axis. So I need to know what this y value is. I'll call it y1. I need to know what this y value is. We'll call it y2. So when I invert that, solve the equations for the respective functions for x, and we change the x and y axis, this is going to look like, let's see, y1 and y2. It's going to intersect at x equals 0, and I'm trying to think of what this is going to look like. I believe this is going to look something like and then this one is going to look something like that. Oops, it's supposed to intersect at y2. Okay, and so the region x equals a is going to become y equals a. That was positive, so that's going to be up here somewhere, right? And now we're revolving this region R about this axis. And so once again, now we're going to do, this time, we look at one large disk we're going to revolve. This is where it comes into play, where you really need to understand the geometry so that you can know which one is going to be your outside disk, which one's going to be your inside disk. And it's all based on the graph and where things relate on the graph. So here, if this was, the blue one was my g of x, right? I guess you could say it's g of y now. We'll go ahead and say that g of y. This is going to be f of y now. Let's go ahead and call them G1 and F1 because they're really not the same functions defined by the same rules since we solved them for y. But so in this case, the length of this rectangle that we're going to use to generate this disk is going to be a minus G1 of y. Very important that we understand the geometry when we're writing these equations and expressing these integrals. So this time, our big disk radius is going to be a minus g1 of y. And of course, the width is going to be dy because we've got a perpendicular y-axis. And so the volume of one of these is going to be pi times the radius squared times dy. And then our smaller disk, let's unclutter that again. Our smaller disk, draw one rectangle that we're going to take out, is going to have a height dy, but this time the radius is going to be a minus f1 of y. And so the volume for that one is going to be pi times the radius squared, a minus f1 of y squared times dy. And the volume of the larger minus the smaller, or the outside minus the inside, is going to end up being our volume that we're looking for. It's going to be the integral. We'll take pi on the outside. We've got y1 to y2, our limits of integration. And then we're going to do the big radius was a minus g1y squared times dy minus the integral with pi on the outside from y1 to y2 of a minus f1 y squared times dy. Understanding the geometry makes all of this make sense. And understand the washer method, where we're doing a region that's not bound by the axis of revolution. We're going to generate the large outside disk with a large rectangle, then a smaller inside disk, and then do the volume of the outside minus the inside. And that's the geometry behind the washer method when we're revolving around axes other than the X and Y axis.